Good afternoon, ladies and gentlemen. I hope your seat backs are upright, your tray tables are stowed, and that your seat belts are fastened. We're going to go through in half an hour quite a bit of technology on the use of microsilica in concrete, how we can best utilize that and other SCMs to get the best quality for our industry. A little bit on global supply and demand, but not very much. A lot of pictures. Comment about volcanic ash. That was good this morning because volcanic ash has been used in the most sustainable building that we've got on the planet. It's been there for 2,000 years. It used volcanic ash and lime to make the concrete. That is quite sustainable. And it's a completely pozzolanic material because they didn't have Portland cement then. So we know this technology, it's been around, we know how to use it. What we need to do is use it better. Silica fume is often thought of as the baby in terms of supplementary cementing materials. We've heard about blast furnace slag, we've heard of fly ash, microsilica, metakaolin and others, and people tend to think silica fume, oh, it's brand new, it's hot off the block. They first collected it in 1947. They started testing it in 1950-52. So we've got 60 years of testing, 7,000 papers of work done on silica fume and silica fume concrete. So we do know a little bit about how it works. Problem was, of course, we're collecting smoke, and smoke means it's difficult to filter. It took a long time to develop the system, but once we developed the system, we could collect in marketable volumes. And of course, once we got marketable volumes, we could start testing it in concrete, in cement blends, and that has led to various standards for the material, which we'll discuss in a second, and of course increasing use in concrete. We're currently looking at around 10 million cubic meters of concrete, high performance, high durability concrete using silica fume around the globe on an annual basis. Now, as you all know, that's a mere scratch on the surface of the total amount of concrete that is produced, which is why we're talking about high performance and sustainability here. Where does it come from? It comes from melting quartz, basically. We take quartz, coke, wood chips as the raw materials, we stick it in a furnace, we light the fire, we get up to 2,000 degrees centigrade, and then we stick an electric arc across it. That gives us some metal. Sorry, the chemists among you, we call it silicon metal because that's how we understand it. The chemists in my company say it's an alloy, silicon or ferrosilicon. That's the stuff that's used in the steel industry, in silicon chip industry, solar panels, all of those sorts of things. Big industry now on the solar panels. What we're interested in is the microsilica. Now, some of you can't see at the back, but down in the bottom right hand corner there's a little scale on that picture. That scale is 1/2 of a micron. That's how small this material is. 100 times finer than cement. And you'll notice that it's all perfectly spherical and it's graded. There's a whole different shape of sizes there. So this enables us to pack the concrete. It enables us to fill the gaps and make a very dense concrete. That's the importance in getting the impermeability and the durability of our concretes that you'll see later on. Now, obviously, it's dependent on the alloy production that they're doing, and there can be a number of different qualities produced by a different plant. It may have 2 or 3 different furnaces, it may have a different filter system on each furnace. And depending on what that is and the filter capacity, that determines the amount of material that we have available around the world. Obviously, the different grades, because of their different qualities, are used in different areas of application. I'll give you that in a second. It all depends on the fineness of the material, the silicon dioxide content. Actually, the flowability of the powder is a very important characteristic. And colour. We can't control the colour, but we can obviously separate out the different colours so that we can blend it with different materials. Some customers like nice dark coloured cements because it gives the concrete a nice dark, strong look. Others prefer light colours because they want to match it in with the existing materials. We can produce the powder as undensified just as we filter it. We can densify it to make it easier to handle, to improve the logistics of moving it around the world. And in Europe we produce it as a slurry, 50% weight for weight, which makes it easier to disperse into concrete much more rapidly. Of course, we don't ship the slurry too far around the world because it's 50% Norwegian water, and nobody wants to pay for 50% Norwegian water if they've got to transfer it halfway around the globe. There are international standards for the product, and these relate specifically to the production source, ferrosilicon or silicon alloy. The Americans always upgrade theirs about once a year, so I just put XX. It saves me keep changing the slide every time. Latest version is always definitive, so even if there's an 04 version that a project has been specified to, it will be the 11 version that we have to supply the product to. And of course we have a European standard, 13263, now being used across Europe and wherever they used to specify to British standards. A lot of British standards now have gone by the wayside because of the ENs coming through, but it's still specified in a number of places, and those are the two that we work to. You've already been told about the European standard where it's mentioned, the European standard for concrete, and of course in the UK, just to be nice, we have to have an intermediate standard, and it's mentioned in that and referenced into 1971 as well. I mentioned 7,000 papers, but we have guides, technical reports, codes, all these sort of things from around the globe for the use of this material. So there is no reason not to look at using it in the concrete or cementitious materials that we produce. There is nothing that says you cannot use this. There's plenty of things that say, yes, you will get a better result if you do. Global supply and demand. Compared to cement production, production of microsilica, silica fume is nominal. There is no need for the cement industry to be scared of this material taking vast swathes of its volumes that it produces around the world. It will only be used for high performance concrete because there's only around 1 to 1.5 million tons of fume produced. That's what comes out of the chimneys. In some areas we can filter that, and at the moment there's only about 600, maybe 800,000 tons that is actually filtered on plants. Of that, maybe 400,000 to 600,000 tons are used. Numbers are a little bit different to the ones in the proceedings because I bludgeoned our R&D department last week into giving me the up-to-date ones. The point is, for instance, China has over 600 plants that produce this material, a fume. Of those, Elkem, the biggest company in the world, work with a handful because of the quality and the volume that they produce and the logistics to actually move it anywhere. So these are the things that we have to consider when we're looking at this product. But that's the sort of amount that's used. And in terms of fibre cement and concrete, they're the two biggest users of cement in the globe. This is the amount that we reckon is roughly used on an annual basis. So those are your sort of numbers that we're talking about. It's not going to scratch the surface of cement production volumes. But if we use it together and we use it with the other SCMs, the blast furnace slag, the fly ashes and other materials, we can produce much better concrete. And the industry will like that. Main applications, as I mentioned, fibre cement and concrete, but it also goes into refractories. Refractories is one of the areas where they want to get maximum strength, maximum impermeability for the least amount of cement they can put in. Therefore they use these materials to improve that quality. Well drilling and polymers are some of the more very specialised areas of use. Just want to run through the fibre cement with you, what we do with that, how it works in that. Of course, most people know fibre cement, nice corrugated sheets that go on low-cost housing, factory warehouses, all of those sort of things, siding boards. And as you can see, a lot in Japan, they use fibre cement for a lot of the housing. Now, it used to be a really easy process. You would mix asbestos fibres and cement and water, put it through the hat check machine, and it would churn out a nice malleable mat that you could then mould into something. It would be nice and strong, it would have a high tensile strength, and it was very long lasting. We know asbestos sheeting is still found around the world that dates well beyond the First or Second World War. But of course, slight problem with asbestos, if it's misused, mishandled, or not treated correctly when you're taking it down, it is toxic. Big move from the industry to rid itself of that. Problem is, it's very difficult to get something that's the same and will react the same. They now have cellulose fibres, PVA fibres, cement, fly ash, and the silica fume, various additives, fillers, and water in that mix to make something that is roughly the same as the old asbestos cement. It works. It works because they can get the bond. The bond to the fibres is the key factor, the important factor. Here you can see what happens as you add different amounts of the silica fume to that mix. You can see that the fibre is virtually uncoated in the first one. A little bit more, 4%, but around 8 to 12%. You've got a very good coating on that fibre. It will bond very well in that matrix, and it will react almost like an old asbestos cement performance sheet. And of course, there's lots of it being used now, changing from the old asbestos cement to fibre cement. So that's one of the big industries that will use it. At the moment, we're not supplying to all of that. There are still major countries around the world that still use asbestos. And of course, the jury is still out on whether you can use it safely or not. We won't get into that argument, but we can do a much better, much safer material. Concrete, my specific area. And we're going to look at some projects now and some use that I hope will encourage you to look at how we can use supplementary cementing materials and get something that our industry and the populace will sit up and look at and say, they did a good job there. That looks interesting. Why aren't we doing that more often? Dual and triple blends, we've already heard about. OPC fly ash and silica fume. OPC slag, silica fume. All the other materials. The mineralins can be used, and rice husk ash, if it's a good enough quality, we can make sure that we can use those blends. Depends on where you are, what's available to design that mix to get the achievement. But we can get greater strength. That gives us physical durability. It also gives us the ability to change designs, to look at designs for buildings and structures and actually build them more efficiently. We can get greater sulfate resistance, greater chloride resistance. Chemically, we can make this material so resistant that it doesn't deteriorate. One of the big problems in the US at the moment is that they have $1 trillion worth of repairs to do to the road and bridge infrastructure of that country because they've used a standard strength of concrete. And of course, things have changed over the last 30 years. Instead of a 10-ton truck going down the road and over that bridge, it's now a 40-ton truck. There's more de-icing salts have gone down than ever before, and of course the concrete deteriorates. They have to look at improving that. But they also have to look at the environment. And New York Council, the state unit of New York Council, has said that you cannot use more than 400 pounds of Portland cement in any concrete per cubic yard. That's not a lot of Portland cement. But they're using blast furnace slag and fly ash and silica fume to still produce 80 and 100 megapascal concretes with ease. If you do it properly and you design it properly, there is no problem. Water resistance, zero water resistance. If water can't get in, nothing else can. Now, of course, in the UK and across Europe, EN 197, there is no sulfate resisting cement anymore. It's not in that standard. If you want it, you have to ask for it specifically. And the cement industry will produce a sulfate resisting cement specifically for you. It's not in the standard. Reason is it's not really that great at sulfate resistance. It slows it down. But 15 years in the sulfate-rich soil in Singapore has destroyed this concrete. That's a 400 cement content SRC mix with a membrane to protect it from the outside, from the ground outside. The other one is a 400 cement content with 10% as part of that cement content of microsilica, in this case silica fume, same thing. And you can see that it looks a bit dirty, but it certainly doesn't have the sulfate attack that this side does. And remember, you're looking at the good concrete on this side. What's behind there resembles a slush puppy. or a snow cone, or whatever, shaved ice, whichever country you come from, whichever term they use for it. That's not very good. That's going to cost hundreds of thousands, if not millions, to replace that tunnel in that busy underground system. We know we can do high performance concrete. We've been doing it since we started collecting this stuff. 2 to 3% is added to the concretes in these particular types of structure to aid the rheology. Remember the picture? It's all perfect spheres. It moves. It adds rheology so you can pump hundreds of meters up into the air. That means that you get a better quality of concrete, better finish on that concrete. And what you can see here, control platform, one of the biggest ones we produced, when they went back and tested the water permeability of this concrete and on others, the average is less than 3 millimeters of water penetration into that concrete. If the water can't get to the reinforcing steel, it cannot corrode it. That's the durability factor. And of course, that means they use it in the roadways. Roadways in Norway, this one's actually a roadway over a bridge as well as the bridge. But they use it, 5 to 10%. It's specified for all infrastructure projects. And concrete roads are coming through very, very rapidly now. And if we start producing a few more concrete roads in this country and other countries, we'll have a lot more concrete to put cement into. It's a very, very big area of use. And it's very much more efficient than asphalt. Lots of information on that. I can give you information on that later. Because if you want a concrete road to be durable, that's what you've got to do. That's how we test it. We get school leavers to try and drive tanks on it. Now you can imagine the damage that that will do to that road surface. But the Ministry of Defence put down 2 areas, 2 tank training bases, Otterburn and Catterick. 20,000 cubic meters of high performance microsilica concrete, silica fume concrete, so that they would get that durability. And they had it dyed grey because they wanted it dyed grey. Concrete, it's going to be grey anyway. Öresund Bridge, 2 different mixes, one from one side, one from the other. Swedish side was OPC and silica fume. Danish side was OPC, 15% fly ash, 5% silica fume. What they had, what they could use to get the performance in the concrete. Of course, the Danish side had already used it in the Storbelt. They'd used over 1 million cubic meters of ordinary Portland fly ash and silica fume blended concrete there. And we did it in India. We've done it all over the place. This is the same sort of thing. OPC, fly ash, and silica fume to get maximum durability in that environment. It's an ocean environment and polluted environment, and they want the durability. They also want the strength to be able to do that. When I first went into India, they said 40 megapascal is all we can do. Can't do anything more than 40 megapascal. By the time I left, going there some 12 years later, they were doing 100 megapascal and not batting an eyelid at doing it. Chiang Mai Bridge in Hong Kong, perfect example of 2 triple blends. OPC fly ash and silica fume for the main abutments, main areas that you can see, but the towers are 65% blast furnace slag, 30% Portland, and 5% silica fume. Believe it or not, that mix at only 390 cement content, total cementitious, achieved over 100 megapascal in long-term strength. The chloride resistance was 10 to the minus 14. That's incredible durability. But because we designed for it, we were able to achieve it. And of course, Hong Kong then took it on. This is the specification for the marine environment. You just need the red lines, 5 to 10% by mass of the cementitious product to get that impermeability. I want to progress on a bit because I don't want to take too much of Dean's time. Dean's been worried about this for a while. Quad blends, all 4, OPC, slag, fly ash and microsilica. This particular bridge used 2 mixes, pre-blended. They were blended off-site, they were shipped to the concrete production units, 2 silos, that's all they needed on site. One silo held one silo held the other. They made a 35 megapascal or a 50 megapascal. Incredible durability required, 100 years in that environment. 32.5 kilometers, they built it in less than 3 years. That's the sort of speed and turnaround we can do. This is the other project in India where they first specified 75 megapascal. This was about 5 years after I'd been trying to persuade them to change the concrete technology, and they did. It's a very strong mix, as you can see from the design there, but look at the numbers that were achieved. At 1 year, that's gone up to 95 megapascal. The chloride resistance is less than 240 coulombs. That's negligible chloride attack on that concrete. They're in the middle of town, but there's still enough pollution there to warrant that sort of durability. Drying shrinkage less than 0.001. This is incredible quality of concrete. And if they can produce it in India, we ought to be able to produce it over here with our quality and design. Number of these things we're seeing around the world in terms of durability characteristics. Specifics. Durability characteristics, not prescriptive mixes. Get the durability characteristics right and look at your strength that you're going to get with that quality of concrete. And make sure the strength resembles what you expect to get. It's no good putting down really low durability characteristics and then putting down 30 megapascal concrete. The ready-mix producer doesn't know what to do with that. He looks at 30 megapascal and looks at 300 cement content. You look at those durability characteristics, you look at a blended cement at about 400. The ready-mix producer needs help, and that's where education comes in. Now, numbers. I spoke earlier on when I made the comment about people looking at cost as opposed to value. 70 floors, they changed the design. Instead of using the tapering column design going all the way through this building, they used the same column size all the way through the building. They changed the strength of the concrete, so the footprint was what they would have originally had. But they changed the strength of the concrete. They used the microsilica, the silica fume, to aid the rheology as they pumped it all the way to the top using one pump. That meant they saved time, they saved formwork, they saved machinery, they saved a volume of concrete. And it meant that everything worked faster. And the owner got more rentable space. And if you think of the numbers that are involved, we were talking about 3,000 tons of reinforcing steel, 7,650 cubic meters of concrete. That's the equivalent of about 3,000 tons of cement. Yeah, I know, that's 3,000 tons you don't have to produce. But you can move that to the next project because we can move faster and more rapidly. It's something in the region of 13,000 tons of aggregates that didn't have to be dug out of the ground or blown up out of the mountain. The environmentalists like that. And I know it's raining outside, and I know we're supposed to be in a drought in this country at the moment, and all the fields are flooded, but water is a very important factor. And on that project we saved over 1 million litres of drinkable water. That's going to be a very important point from the environmentalists in the near future. We can do these columns anywhere. 100 megapascal to do these columns in One Island East in Hong Kong. The only columns in that building are the ones you can see, the central core and the outer 8 columns. There are no other columns in the middle of that building at all. It's all open space because they can do the strength, because they can redesign. And a certain other tall building in Dubai used a lot of concrete. And what are we looking at here? We're looking at a triple blend. We still couldn't persuade them to just use OPC. They had to use a moderate sulfate resistant Portland cement, but there you go. There it is. Moderate sulfate resistant Portland cement, 252 kilos, 168 of fly ash, and a very small amount of silica fume. Those are the criteria that they required. Less than 10% water permeability, less than 5% on a second water permeability test. BS 1881-122, I want someone to scrap that because it's absolutely useless for real concrete. It's done for curbstones, not real concrete. Rapid chloride test, less than 1,200 coulombs. How did we do? Very well. Exceeded the strength criteria, is not a problem. And there are your durability characteristics. 0 water permeability. 0.7 on the water absorption, cut in half. Less than 600 coulombs on the electrical resistance. Chloride resistance to very, very low levels, zero water permeability again. That is durable concrete. That's a triple blend to get the best. It needs to be the best. It's carrying the world's tallest building. They have to have that quality. Very quickly, to run through a few more. Inzua Dam, durability. Built in 1967, repaired in 1974. With a high strength mix made of high cement content, strong aggregates that were shipped in, and steel fibres. Unfortunately, in 1983, this is what the Stilling Basin looked like after that. It had not only worn through the 3 feet, 1 metre of fresh concrete that had been put down in the repair, but 1 foot further into the original concrete. They replaced it with a local aggregate wrapped in a matrix that was Portland cement and silica fume. The bond meant that there was less abrasion, so it's been down there ever since. 67 to 74, 74 to 83, it's been down since 83. In 2008, 25 years on, they found about 3 inches. 3 inches, not 3 foot, but about 3 inches in a few places. That's the sort of durability we've got to be looking at with our projects. We have a few more. Scrapyards are an essential area of making sure we seal the ground and having abrasion resistance, and they use it all over the place. Just want to show you this one because we're talking about 320 cement content. 20% silica fume because they want that ultra durability. They also want 55 megapascal in 48 hours. That's a fast turnaround, but they don't want the slab cracking up in the heat, so they're curing it properly, as you saw in the previous one. Place it, finish it, cure it. Very, very easy. And if you don't believe that sort of durability, how's that for 21 years? B&Q warehouse, trucks every single day. Okay, except for two days during the year, but every single day otherwise for 21 years. That slab is only 4 inches thick. It's made with a 330 cement content, 10% silica fume, and a standard lignosulfonate plasticizer. But you can still see the tining in that concrete. You can still see the arrow-like edges of those slabs. Nothing's crumbled, nothing's deteriorated. That's the sort of durability we're talking about. And it's performance where it's required. Like I said, it's not going to be everyday concrete. There isn't enough silica fume, there isn't enough metakaolin, there isn't enough ricoscash to go around and do everybody's everyday concrete. But if we use it properly, we use it where we know it's going to benefit our design, our characteristics, then we save. Then we save the environment, we make it sustainable, and everybody out there is happy with us because we're showing we're doing something to do with that desire from them to have this environmental safety. The less we repair, the less we need to rebuild. We know it costs less, and we don't have to use those resources. And I'm getting to my point. This is cost money. This is the last few slides, Roy. Cost money. Everybody says, oh, yeah, but that makes the concrete cost a lot more. It costs so much more. That's the concrete. How much does the concrete cost on a major project? What's the percentage? 2-3% of the project cost. This is what people have to remember. And if you don't believe me, I'm going to show you 3 projects now. And if that doesn't interest you, then I'm not really doing my job very well. Green concrete, 311 South Wacker, we've just seen it. Concrete was 50% more per cubic metre. 50% more. We threw everything at it. But everybody had sat around the table to discuss the project. So the ready-mix producer said, yeah, okay, I can charge more for the concrete. And the contractor said, yeah, but you'll supply it faster and you'll supply less of it. But you'll still get more money. Contractor was able to build the building faster because he had the same formwork. His team, he reckoned, could dismantle the column formwork and put it back together blindfold. They got so used to doing it. They were that fast. They used only one pump to pump the concrete. The admixture supplier said, that's fine, we can do a high-performance plasticizer, that will work. The contractor finished the building early, so he got a bonus. The architect got a bonus for redesigning the building, because against the original cost, the new design cost less. And the owner got the building early, and he got more rentable space in the building. So if you do it properly, everybody gets some of that money. We can prove it very easily with sprayed concretes. Mumbai Pune Expressway tunnels, the sprayed concrete, more of it stayed on the wall, less waste, less manpower, less time, faster project. Although it started off at 21% extra per cubic metre, the actual value to the project worked out at 11% less. That's how we make the money. We get a little bit all the way down the line and we save money. Indianapolis Airport parking structure is built for 7,100 cars. Normally, when they build such a structure, the normal design, they work out the cost, and the cost average is $15,000 per space. That's to build the whole structure, works out per space, $15,000. They redesigned the columns, they redesigned the beams and the girders, and they redesigned how they were going to use it. Because they were going to use a high-performance concrete with silica fume, recycled aggregates and other materials, so they got good lead value for this project. They decided that they were going to progress with a new, a faster technique for building it. By the time they'd finished building it, they added up all the cost. And the cost for building it came to only $12,000 per space. Only $12,000 per space. Now there's 7,100 spaces in that car park structure. So whilst you're trying to work out how many noughts to stick on the end of that saving, I'll show you what it looks like. Anybody who can find a car park that looks this clear in the UK, please come and tell me. I will give them £50. But if you can find a car park that has more than 2 spaces or 3 spaces between each column and no low wall in between, then that will be good. Look at the space between the columns. Look at the distance. They only used 60 megapascal. They could have used 100 and slimmed that column down even more. They used 40 megapascal on the deck. They could have done that at 60 or 70 and thinned that girder down even more. The bays are 22 by 20 meters. Vast amount of space. 16 months to build it. 5 floors, 46,500 square meters per floor. Anybody finished doing the calculation yet? $21.3 million. The project saved, through using a properly blended, designed concrete that was highly durable and easy to use, saved $21.3 million. Now, if that's not interesting, guys, then we're in the wrong business. Thank you very much indeed.
Thank you very much indeed, Robert. Are there any questions or points? Yes, both of them.
How do you find the engineering companies? Are they ready? Are they prepared, or are they poorly educated?
To give you for instance, in London, about 5, 6, 7 years ago, I was confronted by a contractor who basically swore at me across the table and wondered why he couldn't get 90 megapascal concrete in London. Because he wanted to use 90 megapascal concrete to redesign the building. The designers know that they can do this, this quality, this strength, they can utilize the strength, they can redesign. The difficulty is the education side again, because this guy had been talking to the ready mixers, and the ready mixers said, no, 70. We top it out at 70. We don't want to do more than that. We won't guarantee more than that. And that's one of the things that we have to work with the education side. When you can see what the numbers are, the numbers we can achieve in terms of water resistance, chemical resistance and things like that, then it slowly works through. The factor is you need somewhere that has a decent pull, if you like. The Middle East, much of that 10 million cubic meters is done out there because there's a pull for it. There's sulfate resistance, there's necessity for chloride resistance, there's a water resistance required, and high strength because of the towers and things they're building, monorails and everything else like that. So there's a pull for that quality of concrete. But it is education. A lot of them are experiencing it now. We have precasters who are doing beams over 120, 150 megapascal. So they can design beams that are 22 meters long and only 400, 500 mil thick, and 1 metre tall, with 3 bands in the top, 3 bands in the bottom, and the rest is made of fibres. But it's so strong and so flexible they can bend it 1/2 metre before it'll crack. That sort of quality of concrete is being designed and being, if you like, slowly brought into the industry.
So you think that the resistance is more from the producer than from the designer?
I would classify it as what we've always sort of said, it's the hassle factor. It's the hassle. We've got to put that in there. We've got to put, that means we need another silo, we need another this. That means we're going to take 30 seconds more mixing or something like that. It's a lot of those difficulties. But if we can work together and you sit around the table, so you have the admixture companies, you have the additive companies, and the producers actually sit down and say, yeah, we can do that.
Then we get excited.
And show it. Then it comes through. Then it becomes much easier.
Yes, please give us your name and company.
Elkem Trading. I understand the silica fume is transported in steel bags on the ship. That increases the costs of handling. But the million-dollar question is still, why is your product so expensive?
Actually, it's not so expensive now. When I first started, it was something like 6 times the cost of cement. Now it's only about 3 to 4 times the cost of cement. And it depends where you're buying it. Obviously, logistics are a considerable point, because you've got a product in the undensified state, you're talking about 200 kilos a cubic metre. That's a lot of volume to transport for the weight. Densified makes it a bit easier. We're working on various things to take the densification higher, but we can't take the densification too high, because otherwise it won't work. If you densify it too much, it won't break down, and therefore you won't get the performance out of it. So we have to balance that. But you are shifting something that's maybe 600 kilos a cubic metre. Transport costs are very, very expensive for that. And again, it comes down to logistics of where the places are that we can shift it from and shift it to. The fact you've got to remember is that when you look at that, it's not what the material itself costs, it's the value of it in the concrete.
There's a salesman answer for you. Okay, I'm afraid that's all we have time for, but
Yes,
once again, Robert,
pudding is...
thank you very much indeed. Thank you.
Thank you.